the end of this chapter. So let us finally see two important things, that is the balance sheet of aerobic respiration and respiratory quotient. Okay. So balance sheet of aerobic respiration, before we begin, you need to know that I'm again reminding 1 NADH is equal to 3 ATP, which all of you know very well. 1 FADH2 is equal to 2 ATP. 1 GTP is of course equivalent to 1 ATP. Why 1 NADH is equal to 3 ATP and 1 FADH2 is equal to 2 ATP, that you have already understood in ETC. So keeping this in mind, let's see the balance sheet. So finally, in aerobic respiration during glycolysis, you know, during the payoff phase by substrate level phosphorylation, directly 4 ATP are produced and 2 NADH will be produced during the dehydrogenation step, and because 1 NADH is equal to 3 ATP, that will be equivalent to 6 ATP. 2 NADH is equal to 6 ATP. So again, also you need to remember that in the activation phase of glycolysis, 2 ATP are already lost, right? So that keeps, or that brings our sum total of glycolysis here to be 4 plus 6, 10 ATP minus 2, bringing it to 8 ATP. So during aerobic respiration, total ATP gained will be 8 ATP. Okay. Now moving to the transition step, which is neither glycolysis nor can it be considered Krebs cycle. So in the transition step, 2 NADH are going to be formed, and that will be of course equivalent to 6 ATP, right? Now finally moving to the last, that is Krebs cycle. In Krebs cycle, 6 NADH. Why? Because there are 2 pyruvic acid formed during glycolysis. So keeping the 2 pyruvic acid, that is equal to 2 Krebs cycle, 2 round of Krebs cycle in mind, we will be having 6 NADH, 2 FADH2 and 2 ATP produced during the Krebs cycle. Okay, by 2 Krebs cycle actually, 2 round of Krebs cycle. So that will be 6 into 3 plus 2 into 2 and 2 into 1, right? Keeping these values in mind. So that will be giving rise to sum total of 24 ATP. Alright, 24 ATP during Krebs cycle will be produced. So that brings you, for aerobic respiration, what will be adding up is 8 ATP from glycolysis, 6 ATP from transition step and 24 ATP from Krebs cycle. Finally, the sum total becomes 38 ATP. So the aerobic respiration would produce at the end of entire thing will be gaining 38 ATP. Of course, in certain of cells, you will be seeing that instead of 38, it can be 36 ATP as well. That's because during glycolysis, the NADH that is formed, this NADH that is being formed in glycolysis, they are going to be formed in cytoplasm. So this NADH to enter from the cytoplasm to enter the mitochondria, they sometimes use certain shuttles, and the shuttles might use 2 ATP. Okay, 1 ATP per NADH will be lost during the shuttle. So if 1 ATP per NADH is lost during the shuttle, so in that case, sum total here will become not 8, rather it will be 6, right? 2 ATP will be lost during the shuttle. So in that case, there will be 2 ATP lost overall. From 38 ATP minus 2, it becomes 36 ATP. Understood? So during in certain of cells, when certain shuttles are being used to transfer the NADH from cytoplasm to the mitochondria, 2 ATP may be lost, and that will bring the sum total to 36 ATP. Do remember that. Now finally, the last topic of this chapter is respiratory quotient. Respiratory quotient is nothing but a ratio. It's ratio between volume of carbon dioxide evolved to volume of oxygen consumed when respiration takes place. It's a value that can be allowing you to understand that what kind of respiratory substrate is being oxidized inside your cell or inside the body. Okay. Now, respiratory quotient for carbohydrate always remains 1. Why? Because during any kind of carbohydrate being oxidized inside your cells, the number of carbon dioxide released is always equal to number of oxygen used. So suppose 6 carbon dioxide are released and 6 oxygen molecules are being used. So 6 divided by 6, that is of course going to be 1. So always for carbohydrate, the RQ value is going to be 1. So in case if you check the RQ of your cells or of your body and it comes out to be 1, you can be sure that what is being oxidized in your cells or in the body is carbohydrate. Okay. Now, followed by fats. For fats, always the RQ is going to be less than 1. Why? Because the number of carbon dioxide that will be evolved will be less than the amount of oxygen being consumed. Fine. Protein is also going to be less than 1 but almost equivalent to 1 because the value will be around 0.9. But for anaerobic respiration, the most interesting part, because in aerobic respiration, oxygen that is being consumed is going to be 0. So no matter how many carbon dioxide is evolved, you divide anything with 0, you get the value to be infinity. So for anaerobic respiration, RQ is going to be infinity. So keep these values in mind. 1 for carbohydrate, less than 1 for fats and protein, and infinity for anaerobic respiration. With that, we come to an end of this chapter. I hope all of you have understood it well. So in the next class, we'll be discussing a new chapter, that is plant growth and development. Thank you.